Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to draw free bodies and apply Newton's laws of motion. So what we're looking at here, right, we've got this biker. She's kind of a thrill seeker here, so she's going to try to grab a ride or steal a ride from this helicopter. So the helicopter is connected to the bike via some sort of light rope. And then the idea is the helicopter is going to fly along and accelerate the biker. And what we're going to try to do is calculate the maximum possible acceleration that this rider could experience and have them stay on the ground. So we're going to start with a free body diagram. Now, this is just a picture of the problem. I don't like I don't like it when we try to turn this into a free body. This is a picture of the problem. When you draw a free body, you take whatever you're drawing the free body of. In this case, it's going to be the biker. Right? What I'm going to do is make another picture of it. What you would do is on your page, draw the biker again. Right? So here's going to be my biker. Now I'm going to start drawing force vectors acting on the biker. Now, when you're drawing free bodies, it's very important to understand how we've defined our system. In this case, my system, I'm going to outline it in green. This is my system here. Oh, I can probably do better than that. This is my system. And when we draw our free body, remember that forces come in two types. We've got field and contact. Right? One of the field forces here is the gravitational force, which is down. Whoops. Now, how we label it, this is up to you. I always label my gravitational force vectors mg. Right. Then look for things coming from outside of this boundary. This is why I bothered to draw this boundary right around my system here. And I'll notice that this rope goes across the boundary right here. Right? That rope is applying a force to the biker. And that force is parallel to the rope. And so maybe something like this. And I normally would label this maybe F sub R for rope, or maybe T because it's a tension. And then here's our 40-degree angle in this problem. Now, also as I look at my green boundary, this surface right here, the ground actually breaks through my green boundary here and applies a force to the biker right at the tires. There's two contacts here and here. These are examples of what we would call normal forces. In this picture, they're applied here and here. This horizontal line really isn't part of the system. If I can get rid of that or not, but again, the system is the biker. And what I'm going to do now is put a normal force in, and that's the force of interaction between the ground and the tire. Now there's two of them. It's quite common in physics to take forces and add them together and call them one force. In fact, all forces really are a sum of many, 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 many forces. All right, so I'm going to put one force vector up. And that's what we would call normal force. If you want to call it force from the road or something like that, that's perfectly fine. Now, if friction were a significant force, that would be to the left. I don't think that's going to be significant in this problem. Air drag, also not a significant force. The tension and the weight and the normal are by far the most important forces. All right. So that's it. We've got our free body now, and now it's about writing equations. So, first equation, and I'm going to use a standard x, y coordinate system for this. We always want to draw our coordinate system because, free bodies are vector quantities, and we use our coordinate system to keep track of vector directions. And Newton's second law, remember, is F equals ma. Now keep in mind in Newton's second law that this force is the net force. Right? It is the vector sum of all forces acting. So in this problem, this allows us to write two equations. Equation 1, if we sum up forces in the y direction, that has to be equal to 0. Now, why 0? Well, if you've seen my video about writing two-dimensional Newton's second law force equations, let's just call it ma for a minute. But the a would be the acceleration in the y direction, or the y component of the acceleration. This biker is not going to accelerate up due to our desire that the biker stays on the ground. So the ma term would be 0 for the y direction in this problem. I'm going to go ahead and call up positive. Now when we write the equation, I take a look over here. The normal is in the y direction, so I'll go ahead and put plus n. The mg is in the minus y direction, so minus mg. Right, the tension. Now the tension has components. I'm going to go ahead and draw them. All right, if I draw the x and y components for this tension, and I like to put my vector components in red, there's the x component. And then maybe something like this for the y component. Oops. And again, it's important to realize these are not new forces. These in red are just another way to think about this. When we're talking y direction, we're talking this one, opposite the 40-degree angle. Now the 40-degree angle is from the tension down to the horizontal. In this picture, that's this angle. So again, the magnitude of that vector is what I'm calling t. So this thing is up, and it's opposite the 40-degree angle. So plus t sine 40, and then equals 0. All right. X direction. Sum of all forces in the x direction equals ma, calling right the positive x direction. Again, my standard rule of thumb for this is identify the acceleration direction, call that positive. This bike is accelerating to the right. Now, as I look at my free body, the normal does not have a force component in the x direction, neither does the mg. The only force component x direction is this one. This component is adjacent to the 40-degree angle, and t is the hypotenuse, so this component is t cosine 40. And it's positive because it points right, and I'm calling right positive. All right, and that's it. This is the only force component in the x direction, so t cosine 40 equals ma. So, important parts of this problem. 1, the free body. 2, this pair of force equations. In this example, summing forces y direction equals 0, sum forces x direction equals ma. All right. 3, now I got to decide, how to implement this rule. So one thing to realize is that if this helicopter, this guy gives it the gas and tries pulling upward, increasing that tension, the normal is dropping. Hopefully, if you're watching this video, you think about this. Eventually, this tension could get high enough that this bike comes right off the ground. If the bike came off the ground, the normal would be 0. So the maximum possible tension is going to correspond to when this goes to 0. So I'm going to take the normal and imagine that it goes to 0. This equation now becomes minus mg plus t sine 40 equals 0. And what I can do from this is solve for the tension now. And what I'm actually calculating is the maximum possible tension while keeping this thing on the ground. So the maximum possible tension is going to equal mg over sine 40. Now what we can do is we can take this and sub it into our other Newton's second law equation. If we do that, what we're going to have now is mg over sine 40 times cosine 40 equals ma. And you notice there's a mass on both sides. So the maximum possible acceleration is equal to g times cosine 40 over sine 40. I'm going to go ahead and write that g over tan 40. Because if I put the cosine 40 in the bottom, sine over cosine is tangent. So I'm going to take a moment here and get us a value and see what we get. And I'm thinking my calculator here is in radian mode, because it gave me a negative number out of that. Okay. And what I get now is about 11.7. I'm getting approximately, if I calculated this right, about 11.7 meter per second per second. or right around 12 meters per second squared. So that looks like about the maximum possible acceleration of that biker while keeping them on the ground. If we wanted to know something about the value of the tension, that's a mass dependent question. You'll notice this maximum acceleration isn't mass dependent, the mass divided out. But if we wanted to know the tension value that gave us that maximum acceleration, that's going to depend on the biker. We can see that basically right from here we would need a mass. So anyway, the purpose of this video was how to draw free bodies, write Newton's second law equations from the free bodies, and that's the majority of this problem. And in this problem we have a little bit of interpretation of one of the equations here, that as the tension gets higher the normal decreases. In this case this normal cannot reverse direction, so the maximum possible tension will occur when that normal goes to 0, resulting in this equation, which then allows us to solve for t sub here and get that acceleration out. I hope this video helps demonstrate these concepts. Have a great day.